Imagine standing on a harbor wall in Liverpool, sometime in the 1820s. Every vessel crowding the dock is made of wood, dark, weathered, creaking timber. The smell of pine tar and salt hangs heavy in the air. This is the only maritime world anyone has ever known. Then, slowly, something moves into the harbor that forces everyone to stop and stare. It doesn't creak, it doesn't smell of timber, and when the light hits its sides, it shines cold gray. It is solid, riveted iron. The sailors on the docks laugh at first. Everyone knows iron sinks, yet here it is, riding the tide just like any other vessel. A few old shipwrights shake their heads in silence. It was a sight that contradicted centuries of shipbuilding logic, appearing just as the physical limits of wood were becoming impossible to ignore. A wooden hull can only grow about 90 meters before its weight destroys it. In heavy seas, the ship twists. The bow and stern droop while the middle pushes upward, hogging and sagging. The flexing rips seams open, causing the ship to break apart. Finding the material was also a crisis. By the 1800s, Europe had built wooden fleets for 3 centuries, and the great oak forests were shrinking. Britain's Royal Navy alone consumed tens of thousands of mature trees per ship, making construction incredibly expensive and politically volatile. Wood is also biological, which means it decays. In warm tropical waters, small marine creatures called shipworms would bore straight through an unprotected hull within months. Even in cold waters, a wooden ship required an army of carpenters for constant caulking and plank replacement. As the Industrial Revolution accelerated, the global economy demanded immense volumes of cargo space. We could no longer rely on a material bound by the biological limits of a tree and the physical ceilings of timber. Engineers found a middle path before fully committing to a new material. They built composite ships, vessels with a rigid internal iron skeleton wrapped in an external skin of wooden planking. Some of the most famous vessels of the 19th century were composites. The Cutty Sark, launched in 1869, survives today as a prime example of this hybrid design. The iron frames were exceptionally strong and light, allowing ships to grow longer and carry more cargo without sagging. The wooden outer planking, meanwhile, served a very specific purpose. It allowed builders to attach copper sheathing to the hull to protect against shipworm. Trying to attach copper directly to bare iron in salt water causes rapid chemical corrosion. Composite construction gave shipbuilders the rigidity of metal and the biological resistance of wood, serving as a vital stepping stone between the ancient craft of woodworking and heavy industry. The British engineer Isambard Kingdom Brunel forced the maritime world to take the final leap. In 1843, he launched the SS Great Britain. At nearly 100 meters long, she was the first large ocean-going vessel built entirely with an iron hull. Her scale proved that massive metal ships could survive the open sea. This cross-section shows the new logic of ship construction. Shipwrights abandoned carved, overlapping wooden planks. Instead, they built a mathematical grid of longitudinal girders, running the length of the hull, crossed by transverse metal frames. Once iron proved itself, shipbuilders quickly adopted a superior alloy, steel. The invention of the Bessemer process in 1856, blasting molten iron with air to burn off impurities, made it possible to produce strong, flexible steel cheaply and quickly. By riveting metal plates onto a rigid internal grid of cheap steel, engineers broke the physical constraints of timber. The maximum size of a ship was no longer dictated by nature. But iron and steel introduced challenges no shipbuilder had ever faced. Wood rots, but iron rusts incredibly fast in salt water. This chemical corrosion eats through metal plates until the hull is severely weakened or breached. To combat this, engineers developed new protective paints and installed sacrificial zinc anodes, small blocks of zinc attached to the outside of the ship. Because zinc corrodes more easily than iron, the salt water destroys the blocks instead of the hull itself. The construction process also required an entirely new type of labor. You cannot shape steel in a quiet coastal boatyard with hand tools. It required blast furnaces, massive rolling mills, and armies of men driving hot iron rivets through overlapping metal plates. Sprawling industrial complexes rose along rivers like the Clyde and Glasgow to meet these manufacturing demands. Tens of thousands of workers, organized in strict trades, labored under towering cranes to assemble metal skeletons. Solving the bottlenecks of the wooden hull inadvertently gave birth to the brutal, deafening, heavy industry shipyard of the modern era. The massive scale of these new vessels caused an immediate economic explosion. Where a wooden sailing ship carried a few hundred tons of cargo, a steel vessel from the 1880s could carry 10,000 tons. The cost of moving wheat, coal, and tea plummeted, making global commerce a daily routine. Navies were forced into rapid modernization. Wooden fleets were scrapped in favor of heavily armored ironclads. Wood had absolutely no defense against iron cannonballs fired at iron hulls. For millennia, a ship was an organic object carved by craftsmen. Now it was a standardized, rigid industrial product that conquered global distance. The metal hull solved the problem of scale, but it created a new one: weight. To move 10,000 tons of steel and cargo across an ocean on a reliable schedule, wind power was no longer enough. Deep below the decks of these massive, heavy new ships, engineers were already fitting enormous boilers and pistons. Coal and fire were now ready to replace the wind. They simply needed a hull strong enough to hold them.